Today we're going to start section 6 of chapter 2, implicit differentiation. All right, so up to this point, we've covered quite a few techniques of how to find the first derivative or derivative with respect to x. Starting with the sum and difference rules, moving on to the product and quotient rules. And lastly, we went over the chain rule, which is how we define a function in a function. Or another way of thinking of this is a function that is described in another term other than the variable that we're focusing on. All right, so implicit differentiation is another technique of finding the derivative of y with respect to x. So ultimately, we're still looking for the first derivative of y with respect to x, or we're still trying to find a derivative. Now, up to this point, we've always dealt with equations that have been explicit in form. So we're going to first take some time to see the difference between an explicit equation. An example of an explicit equation, y is equal to the square root of x cubed plus 1. We know this is an explicit equation because they explicitly tell us what y is in terms of x and x alone, outside of the operations of the numbers themselves. So we have y equals something or some expression written in terms where x is the only variable that we're focusing on. Another example of an explicit equation that we've dealt with, y is equal to x times the sine of x. Now we're looking for the derivative. This will be a product rule problem. Obviously, we have to use the derivative of trigonometric functions to find the derivative of sine x. This is another example of an explicit equation. This is because they're telling us what y is in terms of x and x alone. So a good way of trying to figure out that we have dealing with an explicit equation is if the equation starts with y equals or f of x equals, with understanding that f of x and y are the same thing. So these are examples of explicit equations. An example of an implicit equation would be something like so. Let's say x squared plus y squared is equal to 25, or x cubed plus y cubed is equal to 6xy. All right, so these are examples of implicit equations. A good note of when we're dealing with an implicit equation, you'll see x and y on the same side of the equation, or it's not easily manipulated to where we can isolate y by itself. Like here, if we had x squared plus y squared is equal to 25, yeah, we could solve this for y, but we end up with an equation that has two options. All right, or more easy way of thinking of it is not easily solved to get y by itself. So if we don't see y equals something in terms of x and x alone, then we know it's not an explicit equation, it's an implicit equation. And if it's an implicit equation, we can solve it or solve for the derivative implicitly by using the technique of implicit differentiation. All right. So first, let's define what implicit differentiation is. It's technically building on the chain rule. All right. So implicit differentiation, by definition, implicit differentiation consists of differentiating both sides of the equation with respect to x, and then solving the resulting equation for y prime. So even though they don't tell us explicitly what y is in terms of x and x alone, with implicit equations, we can take derivative with respect to x for both sides of the equation, as long as we remember the chain rule. All right. Now, the chain rule says that if we have one function in terms of another function, or a function inside of a function, then we must take the derivative of the outer function at the inner function times the derivative of the inner function. Remember, that was that shorthand definition of the chain rule. The formal definition was a little more involved. As far as implicit differentiation goes, if we remember this one thing, then we don't have to worry about applying, or excuse me, we will be still applying the chain rule. But if we remember this one rule, we can get around it. Let's not think of it as applying the chain rule. All right. So if we're solving it implicitly, which means that we're dealing with implicit equations, or they do not explicitly tell me what y is in terms of x and x alone. Then we're going to apply implicit differentiation. And anytime we apply implicit differentiation, we must remember that every time we take the derivative of y, or something defined by y, we must attach either dy, dx, or the first derivative of y with respect to x in the Leibniz notation, or y prime, which is another way of writing the first derivative of y with respect to x. This is the Newton notation. All right. So if we're solving it implicitly, or we're applying implicit differentiation, every time we take the derivative of something defined by y, we either attach dy dx or y prime to it. All right. So in example 1, our first opportunity to use implicit differentiation. We have 2 parts to example 1. First part, it says if x squared plus y squared is equal to 25, find dy dx, or find the first derivative of y with respect to x. And for part 2, or part B, find an equation tangent to the circle x squared plus y squared is equal to 25, specifically at the point 3, 4. Right. So for part B, it will help for us to remember that the first derivative is the slope of the tangent line. We're asked to find the equation. So we're going to end it with an equation that represents the slope of the tangent line at the point 3, 4. All right, so once we find dy dx, or that first derivative of y with respect to x, implicitly, we have to remember that that is the slope of the tangent line at any point. So if we wanted to find the slope of the tangent line at a specific point, let's say 3, 4, we just make the appropriate substitutions. All right. So for part A, we need to find the first derivative with respect to x, or dy dx. Given that x squared plus y squared is equal to 25. All right, so first, we want to recognize that this is an implicit equation. Remember, the way we can tell it's implicit, it does not tell us what y is specifically in terms of x and x alone. So we don't see y equals yada, yada, yada with x in it. So because we have x and y on the same side, which is another telltale sign for an implicit equation, we must solve this through implicit differentiation. Remember, we're looking for dy dx. First step, we're going to have to take derivative with respect to x, or ddx, of both sides of my equation. So we're going to be looking for ddx of x squared plus y squared. And that's still going to be equal to ddx of 25. We can apply the sum rule, saying that the derivative of the left-hand side, we'll be looking for ddx of x squared plus ddx of y squared, or we can take the derivative with respect to x of each element on the left-hand side, and we know the derivative with respect to x of any constant is going to be 0. Now, the only issue that we really run into here, or why we have to solve this implicitly, and remember that one additional rule. If we're looking for the derivative with respect to x of x squared, not a problem. This is written in terms of x. Even if we had ddx of 25, which is a constant, that's understood to have 0 x's. So there's no other variable. We can still take the derivative with respect to x of 25 as well. The issue is, when we're taking the derivative with respect to x of something written in terms of y, that's a different variable. All right. So we can't take the derivative with respect to x of y squared, at least without remembering the chain rule. All right. Now, in this problem, I'm going to show you why, or explicitly why we have to attach that dy dx when we take the derivative of something defined by y, by applying the chain rule. But remember that as long as you remember to attach it, you don't have to really know the minutia of why we're doing it. So we want to remember that y is a function of x. we can apply the chain rule, or we use chain rule here. So technically what we're looking for is d dx of y squared, or derivative with respect to x of something defined by y. Now, because it's defined by y, we really have to take the derivative with respect to y because that's the variable. So what we're doing is taking the derivative of the outer function, which would be that function defined by y, at the inner function, but we got to remember to multiply by the derivative of the inner function. So we've got to take the derivative with respect to y of something defined by y. This is us attaching that dy dx or y prime. So remember, as long as you remember to apply or attach dy dx or y prime, when we're taking the derivative implicitly to anything defined by y, we can keep on working with no issue. So the derivative with respect to y of y squared, we can apply the chain rule, or excuse me, the general power rule. Derivative of y squared, bring the exponent out front, decrease the exponent by 1. So the derivative of y squared would just be 2y, and then we must attach that dy dx because we took the derivative of something defined by y. All right, so picking up where we left off in the original problem, taking this derivative, now that we know what we're going to get to this part, the derivative with respect to x of x squared, still applying that general power rule, that's going to give me 2x plus the derivative with respect to x of y squared would be 2y dy dx. And that's still equal to the derivative with respect to x of 25, or 0. So we've taken the derivative with respect to x on both sides. Now we can solve for dy dx. And notice how we have one singular positive dy dx in our equation. So really, we're just trying to isolate that dy dx. First thing I would do is subtract 2x from both sides of my equation. This is going to give me 2y dy dx is equal to a negative 2x. And then to get dy dx by itself, we can divide both sides by 2y. This way the coefficient cancel, leave me with dy dx, what it is we're looking for. The 2's would cancel because anything over itself cancels, leaving me with a negative x over y. So the slope of the tangent line at any point would simply be negative x over y. All right, so we're done with part A. In part A, we're just trying to find dy dx. We got dy dx by itself. For part B, we're asked to find the equation of the line tangent at the point 3, 4. So one, remember that the slope of the tangent line, or m tan, and dy dx, the derivative with respect to x, are the same. They are equal to each other. But we're looking for this at the point 3, 4. So keeping in mind that dy dx is negative x over y. We're looking for it at the point 3, 4. This implies that x is 3 and y is 4. All right, remember that point is going to be on the curve of the original function. Remember, we're trying to find the slope of the tangent line to that point. So if this is the slope of the tangent line at any point, and we're looking for it at the point 3, 4, the slope of the tangent line we're looking for, our m tan would be negative x over y, or negative 3/4. Now remember, part B asks for us to find the equation of the tangent line. We have the slope and we have a point that the tangent line goes through. Remember that point 3, 4. Slope we just found to be negative 3/4. So we can label this as x1 and y1, and we can use our point slope formula. Y minus y1 is equal to m times x minus x1 to get an equation of that tangent line. Now remember, there is a couple of ways we can write the equation. We can write it in slope-intercept form. We can write it in standard form, or we can write it in point slope form, like we have here. So if this is x1, this is y1, we have our slope, plugging everything in its appropriate place. The y minus y1 is equal to our slope times x minus x1. And we'll have y minus 4 is equal to negative 3/4 times x minus 3. Now, this is a test question. This is technically an equation of the tangent line. It's not the only representation, but this is probably the quickest way to get a correct answer. This is the point slope form of the equation of the tangent line. Now, to stay consistent with the book, we want to write it in a standard form. After this point is really just manipulation with algebra. So, like I said, if this is a test question, this will get you full credit. So we have y minus 4 is equal to negative 3/4 times x minus 3. First thing we could do, go ahead and distribute that negative 3/4. So give me y minus 4 is equal to negative 3/4 x. Negative 3/4 times negative 3 would be plus 25/4, which will actually be the fraction we'll get by multiplying negative 3/4 and oh, I'm sorry, skip a step. That should be 9/4. Should be y minus 4 minus 3/4 plus 9/4. And to get the y by itself, we'll have to add 4 to both sides. Or we'll have y is equal to negative 3/4 x plus 9/4 plus 4. Or we could rewrite this as 16/4, which will give me 25/4. Now this is technically the answer, or excuse me, the slope. Excuse me one more time. This is actually the equation of the tangent line in slope-intercept form. This is point slope. Either one of these two will get you full credit. Remember, there's a bunch of different ways you could write the equation, but there is an equation of that tangent line. And the last form is actually standard form, which is ax plus by is equal to c. Or I'll have to move the x term over with my y by adding 3/4 x to both sides. This will give me 3/4 x plus y is equal to 25/4. And in standard form, we don't want any fractions. So the easy way to handle that is to multiply everything in the equation by 4 on my denominator. So I'll have 3x plus 4y is equal to 25. And this is the equation, or an equation of the tangent line in standard form. All right. I did want to just go over those forms because odds are if we have any more equations or problems like this, I'll just give it to you in one of them. And once again, you'll get full credit by putting it in point slope. So I really don't see why anybody would go past this form, because it gives you a lot less opportunities to make a mistake. Any questions on example 1? All right, so with implicit differentiation, like we said before, anytime we take the derivative of something defined by y, we must attach either dy dx or y prime. All right, so first, we want to identify if it's explicit or implicit. Obviously, if it's explicit, we got a few techniques. If it's implicit, we'll see x and y on the same side of the equation, or it's going to be an equation that's not easily manipulated to get y by itself. All right, once we understand that it's an implicit differentiation problem, all the other techniques are still can still come into play. So in example 2, here we're asked to find y prime. If x cubed plus y cubed is equal to 6xy. All right. Now, in order for us to find, one, we want to recognize that it's an implicit differentiation problem. It does not explicitly tell us what y is in terms of x and x alone. So this is an implicit differentiation problem. For the left-hand side, we can just take the derivative with respect to x, and it won't be an issue. This one's defined by x cubed, so we just apply the general power rule. And as long as you remember to attach either dy, dx, or y prime, in this case, I'll probably attach a y prime because that's what we're looking for, then taking this derivative, or the derivative of y cubed, isn't really an issue either. Now for the derivative of 6xy, That's the product of two differentiable functions. Me personally, I would look at it as 6x as the first differentiable function and y as a second differentiable function. So in order for us to find the derivative of the right-hand side, we would have to apply the product rule, or f prime g plus f g prime is one way of analyzing the product rule. All right. So if it were me, I would actually start on the right-hand side first, getting this derivative, because it's going to take the most effort applying the product rule, keeping in mind that if we take derivative of something defined by y, we attach the dy dx to it. All right, so focus on the right-hand side first. My first differentiable function for 6xy, or f, will be 6x. My second differentiable function, or g, will be y. We still need to find f prime and g prime, respectively. So given that f is 6x, f prime, or the derivative of f with respect to x, would just be 6. Given that g is y, the derivative of g with respect to x, the derivative of y would be 1. But remember, because we're solving this implicitly, anytime we take derivative of something defined by y, we must attach a y prime. All right, and 1 times y prime, we could just look at that as y prime itself. So we have f 6x g y. We found f prime 6, and we found g prime, which is y prime. So now all we have to do is plug everything in its appropriate place in the product rule and continue differentiating on our problem. So remember, the left-hand side wasn't supposed to be an issue. So the derivative of x cubed, 3x squared, plus the derivative of y cubed, that would be 3y squared. And remember that we're taking the derivative of something defined by y. So we must attach a y prime. It's going to be equal to the derivative with respect to x of 6xy. That's what we're working on. It's f prime g, or 6 times y, 6y, plus f g prime, or 6x times y prime, which would be 6xy prime. All right, so we're taking the derivative with respect to x to both sides of my implicit equation. The first thing I would do to help simplify is recognize that every one of these terms have a coefficient that's divisible by 3. So I'll reduce everything by 3. I'll divide everything in the problem by 3, which will give me x squared plus y squared y prime is equal to 2y plus 2xy prime. So now we can solve this for y prime. Unlike the last example, we don't just have one term with y prime in it. We actually have 2 terms with y primes in them. So what we want to do is get the y primes on the same side. For me, I'm going to bring this 2xy prime to the other side of the equation by subtracting it. And I'm going to take the terms without y prime, here x squared and 2y on the same side. I'm going to move the x squared to the other side by subtracting it. All right, so on the left-hand side, I'm going to have y squared y prime minus 2xy prime. And that's going to be equal to 2y minus x squared. So now that we got the terms with y prime on the same side, we can factor out a y prime. Both of these terms have at least one y prime in common, so I can pull out y prime, leave me with y squared minus 2x inside my parentheses, and that's going to be equal to that same 2y minus x squared. And then I can just divide both sides by the coefficient, or in this case, the y squared minus 2x. So y prime ends up being equal to 2y minus x squared divided by y squared minus 2x. Any questions on example 2? So remember, with implicit differentiation, that's one more technique, but it's still holding us true to all those other techniques, like product rule, or for example, the next problem, or next example, should I say, chain rule. Anybody see a copy from up here? All right, so in example 3, more the same, still dealing with implicit differentiation. Example 3, we're asked to find y prime if the sine of x plus y is equal to y squared times the cosine of x. All right, so just like in the last test, I was saying that when it comes to these derivatives, any one technique in and of itself is not that difficult. What becomes the real problem is knowing when to use what technique. So if we look at the left-hand side of this equation, the sine of x plus y, it should be obvious at this point that this is an implicit equation. It does not start with y equals or f of x equals, and then give us an expression in terms of x and x alone. But on this left-hand side, we have the sine of x plus y. Had this just been the sine of x, we know how we could take the derivative by just simply pulling it off our chart. So we have the sine of x as my outer function. My inner function will be x plus y, or what's inside my parentheses. So this is actually a chain rule problem. Or if we had to find a derivative, which is what we're going to have to do here, this will actually be a chain rule problem. You have an inner function or a differentiable function on the inside, x plus y. We could solve that implicitly with no problem. And the outer function will be sine of x. We could solve for the derivative of that just by pulling it off chart. On the right-hand side, we have two differentiable functions, y squared and cosine x. This is a product rule. We have two differentiable functions that are being multiplied. So this is a product rule problem. So though we're going to take the derivative with respect to x on both sides, the way that we're going to take the derivative is going to be different. One side we have this chain rule, the other side we have this product rule. Now, provided that we understand that shorthand definition of the chain rule, the derivative of the outer function at the inner function times the derivative of the inner function, and the trigonometry or the derivative of trigonometric functions or how to handle them isn't an issue, that we can solve that left-hand side without very much work. The right-hand side, though, the product rule, we're going to have to label F, label G, find F prime and G prime, as well as plug everything in its appropriate place. All right. So just to be clear, and I do want to make sure we had this in our notes, we're taking the derivative with respect to x of the sine, bracket, of x plus y. And then we're still taking the derivative with respect to x of y squared times the cosine of x. So essentially, we're still taking the derivative with respect to we're still taking the derivative with respect to x on both sides. On the left-hand side, the inner function was x plus y. My outer function, sine x. That shorthand definition of the chain rule, derivative of the outer function at the inner function, derivative of sine, cosine, at the inner function means what was inside the parentheses. It's going to go inside the parentheses again. So this is the derivative of the outer function at the inner function times the derivative of the inner function. Remember, my inner function here, x plus y. Keeping in mind that we're taking this derivative implicitly. The derivative of x with respect to x, 1, plus the derivative of y with respect to x. The derivative of y will be 1, but because we're solving this implicitly, anytime we take derivative of something defined by y, we must attach a y prime. Now for the right-hand side, like we said before, it's going to be a little more involved. I need to label F, G, find F prime and G prime. With me, my first differentiable function, f, will be y squared. Second differentiable function, g, that will be cosine x. Given that f is y squared, f prime, derivative of y squared will simply be 2y. We're taking the derivative of something defined by y, so we must attach a y prime to it. Given that g is cosine x, g prime, derivative of cosine, negative sine. So derivative of cosine x, negative sine x. So we have f, g, f prime, and g prime. Remember the product rule, f prime g plus fg prime. So plugging everything in its appropriate place. F prime g are 2y y prime times cosine x plus f g prime y squared times negative sine x. And it's still equal to that derivative on the left-hand side, which we have found to be cosine of x plus y. And still needs to be multiplied by the derivative of the outer function, 1 plus y prime. All right, so now we can start simplifying. We've already taken the derivative with respect to x on both sides, applying both the chain and product rules appropriately. The most common mistake that I see from here on out, most people, when they're starting to deal with this, or at least in previous classes, should I say, when they see that cosine of x plus y times 1 plus y prime, they have a tendency to think of this as two binomials being multiplied, or they want to FOIL it out because they say parentheses and the parentheses. Remember, the cosine or all trigonometric functions have to have something in which they're taking the function of in order for it to be a value. So cosine doesn't mean anything. You must have cosine of something. So that's why we say cosine x or cosine x or sine y. So when we have the cosine of x plus y, this looks like a binomial, or it looks like it's two terms, but it's actually just one. So we're not foiling, we're actually distributing. So we must multiply both 1 and y prime by the cosine of x plus y. So cosine of x plus y is just one term. So the cosine of x plus y times 1, that's going to give me the cosine of x plus y, because anything times 1 is itself. And then the cosine of x plus y times y prime will give me a positive y prime cosine of x plus y. And this is equal to 2y y prime cosine x minus y squared sine x. And there we're just multiplying, making sure that we put the coefficients in front of trigonometric values. Here, positive times a negative is going to give me a negative. All right, so we've taken the derivative and simplified with respect to x. What we need to do now is solve for y prime, or get the terms with y prime on one side, the terms without y prime on the other. Now, though these terms are pretty intricate, we only have 4. The first one, cosine of x plus y. The next, y prime cosine of x plus y. After that, 2y y prime cosine of x. Then lastly, that negative y squared sine x. So we have 2 terms with y primes in them, and we have 2 terms without y primes in them. All right, so now what we want to do is get the terms without y primes on one side. For me, I'm going to bring this y prime cosine of x plus y to the other side of my equation by subtracting it. And I'm also going to bring this negative y squared sine x to the other side by adding it. There's no rule saying that you have to do it that way. I just don't want to have to deal with any negatives. So on the left-hand side, I'm going to have the cosine of x plus y plus y squared sine x, getting the 2 terms without y primes in them on the same side. On the right-hand side, I'm going to have 2y y prime cosine x minus y prime cosine of x plus y. Now on the right-hand side, I can factor out a y prime. So left-hand side is going to stay the same, cosine of x plus y plus y squared times sine x is equal to y prime. I'm going to want to factor out inside my parentheses 2y cosine x minus cosine of x plus. Right. And now I just need to divide by the coefficient, or that 2y cosine x minus cosine of x plus y. This is why I'm getting the y prime by itself. So y prime will be equal to the cosine of x plus y squared sine x divided by 2y cosine x minus the cosine of x plus y. Okay. Any questions on example 3? All right, example 4. Just like in the other techniques, we have to go over higher order derivatives as well. This time in example 4, we're asked to find y double prime. If x to the 4th plus y to the 4th is equal to 16. Put a star on this one. Typically the algebra in this problem, the fact that we have to mix the quotient rule, take higher order derivatives, and remember this overall statements that have shown up in this problem. Typically, you have to mind around this one. The other 3 are the issue. All right. So first, we need to recognize that this is an implicit equation. So we're going to have to solve it through implicit differentiation. I'm going to take the derivative of both sides of this equation with respect to x. All right. So the derivative of x to the 4th with respect to x, 4x cubed plus the derivative of y to the 4th with respect to x, before y cubed, and we got to remember to attach y prime to it, or dy dx. This time we're going to choose y prime. And this is going to be equal to the derivative with respect to x of 16. We know derivative of any constant. It's going to be equal to 0. Now we can solve this for y prime by subtracting 4x cubed from both sides. So give me 4y cubed, y prime is equal to negative 4x cubed. And to get the y prime by itself, we must divide both sides by 4y cubed. So it's going to leave me with y prime is equal to negative x cubed over y cubed. Another way of looking at this, y prime is negative 1 times x cubed over y cubed. But we're just pulling out that constant multiple. It's understood to be negative 1. All right. So we solve for y prime. Remember, we weren't asked for y prime. We were asked for y double prime. So we must take the derivative of other derivative. But in order for us to do that, we must first find the first derivative. Now, this is going to help with the algebra, or at least in previous classes it has. Instead of us looking at y prime as negative x cubed over y cubed, that negative, when dealing with all the algebra, especially with the substitutions that we're going to have to make, has been an issue. We're just going to remember that we have a scalar multiplier or a negative 1 out front. This way, when we're taking the derivative of y prime, my first differentiable function is a positive x cubed. My second differentiable function is a positive y cubed. All right, so in order for us to start working on that second derivative of y double prime, we're going to need to label f, g, find f prime and g prime. This is a reminder, quotient rule. F prime G minus F G prime has all been divided by G squared. I remember I always do this with the Newton notation. It seems to be a little simpler than the Lebanese notation. All right. So my first differentiable function, F, that would be x cubed. My second differentiable function, G, that would be y cubed. Still need to define F prime and G prime respectively. So given that F is x cubed, F prime would be 3x squared using the general power rule. And given that G is y cubed, G prime would be 3y squared, y prime. Remember that anytime we take derivative of something defined by y, we must attach a y prime to it. So we have F, G, F prime, and G prime. I want to remember that when working with this derivative, that we do have a scalar multiplier of 1. So I'm just going to stick this negative 1 out, of negative 1. I'm just going to stick a negative 1 out front. This way we can just focus on the product rule part of this problem. So we have F prime G minus F G prime. F prime G, or 3x squared. F prime G, y cubed, minus F G prime, F x cubed, times G prime, which is 3y squared, y prime. All of this is being divided by G of x squared, or in this case, y cubed, which is G of x, raised to the second power. Keeping that negative 1 out front. That's going to give me 3x squared y cubed minus 3x squared, 3x cubed y squared y prime, and all this is going to be over y to the 6th power. Which is y cubed raised to the 2nd power. We just multiply those exponents. All right. Now this is where we're going to make our first substitution. We want to remember that y prime is negative x cubed over y cubed. So if y prime, which we already found to be negative x cubed over y cubed, if that's true, we can make that substitution right here. So this y prime is going to change to negative x cubed over y cubed, and then we're going to continue simplifying. All right, so we still got that negative out front. Being multiplied by 3x squared y cubed. Sorry about that, I said cube root 2. Minus 3x cubed y squared is being multiplied by negative x cubed over y cubed, which is y prime, and all this is still being divided by y to the 6th. So all we did was make that substitution for y prime, which is negative x cubed over y cubed. All right. Still have that negative out front. For this product, 3x cubed y squared being multiplied by the quotient negative x cubed over y cubed, we can multiply that and do some simplification. Up top, we still have that 3x squared y cubed. We haven't really touched that yet. we're subtracting this product. If we have a positive times a negative, we're going to be subtracting a negative. So let's say that minus becomes a plus. 3x cubed times that x cubed up top will give me 3x to the 6. This y squared in my numerator is being divided by the y cubed in my denominator. We can subtract the exponent because the bases are the same. So we're going to end up with just a y in the bottom of that fraction. All of this is still being divided by y to the 6.
What you said about how we got y to the first now?
Right here. All right, so we're multiplying these two terms. Well, one, we got a negative and a negative. That's how it became a positive. This way we don't have to worry about the now, the integer signs. So we got 3x squared times that, 3x cubed times the additional x cubed. That's how we got 3x to the 6. So we really have 3x to the 6 up top, y squared over y cubed, right? These bases are the same, these y's. So these two y's cancel out with 2 of the 3 y's in the bottom, leave me just with y on the bottom. So that's how we ended up with that 3x to the 6 over y here. All right, did I answer your question? Are you got any other questions up to this point?
Yeah, when you multiply exponentials, you're adding, right?
Mm-hmm.
So why did you get y6 for the bottom when it should be 5?
We're talking about this y to the 6?
Yeah.
That came from, yeah. Remember that came from the previous stuff. That y to the 6 we really have to touch. This y to the 6 on the bottom, the one you're talking about, came from that g of x squared. Remember, g of x was y cubed. G of x squared would be y cubed squared, which gives me that y to the 6. All right, any other questions? Though, like I was saying, the algebra in this problem is really going to be the issue. So it's a lot of little places where you can make a small mistake. Any other questions up to this point, though? All right, so still simplifying using our algebra. The way that I choose to look at this, we have a whole number, 3x squared y cubed, plus a fraction, 3x to the 6 over y. We can easily turn this whole number into a fraction by putting it over 1. So now we have 3x squared y cubed over 1 plus 3x to the 6 over y. All of this is still being divided by y to the 6. And the reason that I like to do it this way is because now we can think of, we're adding or subtracting fractions, so we can use that flying X technique. Top left times bottom right, take the sign in the middle. Here we're adding, so we can add. Bottom left times top right, and it's all over the bottom times the bottom. So here we got 3x squared y cubed times y, which will give me 3x squared y to the 4. Plus bottom left times top right, 1 times 3x to the 6. That's going to give me 3x to the 6. It's all over the bottom times the bottom. 1 times y would just give me y. It's all over y to the 6 still. So it's focusing on what's inside the parentheses, still simplifying. Now we have a fraction, pretty complex fraction, 3x squared y to the 4th plus 3x to the 6 over y. That's my top fraction being divided by a whole number, y to the 6. Just like before, we can easily turn that whole number, y to the 6, into a fraction, putting it over 1. This way we can use that keep, change, flip. So we're going to keep the top fraction the same. 3x squared y to the 4th plus 3x to the 6 over y. Change division to multiplication and flip our bottom fraction. Y to the 6 over 1, now 1 over y to the 6. So that's going to give me the fraction 3x squared y to the 4th plus 3x to the 6 over y to the 7. All right, all we deal with multiply the top. Anything times 1 is itself. In the bottom, we have y to the first times y to the 6, which gives me y to the 7. Question?
Five, 6, it's still at the bottom. I thought that was supposed to be 1.
Yeah, it is. Remember, we do the keep change flip, so we keep this fraction the same, change division multiplication, and then we did flip it to 1 over y to the 6, right?
I thought like everything.
Say that one more time.
I thought like that whole fraction of both 12 and 6.
Right here.
Yeah, I thought all of that was like the
Right. So this the fraction. This top fraction stays the same. It's all over 1 y to the 6, but we change this whole number y to the 6 into a fraction by putting it over 1. This way we have a fraction divided by a fraction, and we can do the keep change flip, because technically you can't divide a fraction by a fraction in algebra. You want to divide it by you divide a fraction by multiplying by the reciprocal. Instead of saying that every time, we always just say keep change flip. So we kept it, changed it, flipped. All right. Any other questions up to this point? All right, so now we have our numerator. Understand that we still have that -1 out front, and we're going to start simplifying by factoring here. We have our numerator 3x squared y to the 4th plus 3x to the 6th, all being divided by y to the 7th. Up top, my two terms, they both have at least 3x squared in common. So we can actually pull that out. So we have the -3x squared as my GCF being multiplied by y to the 4th plus x to the 4th. All this is still being divided by y to the 7th. And this is when we want to remember that x to the 4th plus y to the 4th is equal to 16. Remember, this was our original problem, which is very much understandable for you to get at this point. When we started with this equation, x to the 4th plus y to the 4th is equal to 16. X to the 4th plus y to the 4th, same thing as y to the 4th plus x to the 4th. So we can make this substitution, replacing x to the 4th plus y to the 4th with 16. So we have a -3x squared times 16 over y to the 7th. Our answer ends up being -48 times x squared over y to the 7th. And this is y double prime. All right. The homework for this section, if you're in the 8th edition, starts on page 167. I want you to do problems 5, 23, 25, 35, and 37.